Good afternoon, everyone, and welcome to the EOL seminar series. Our speaker today is EOL's very own Dr. Holger Vömel. Currently, Holger is a scientist at EOL's in situ sensing facility, heading the research and development of the AVAPS Dropsonde group. Dr. Vömel is no stranger to balloon-borne observations and has made a lifelong career in launching, collecting, and studying observations from all types of soundings, including, but not limited to, dropsondes, radiosondes, ozone sondes, and water vapor soundings. Essentially, he is EOL's resident expert in soundings both up and down. A native of Germany, Holger holds degrees in physics at the universities of Frankfurt and Heidelberg, finishing with a PhD at the University of Colorado. Dr. Vömel has divided his research tenure between Germany and Colorado, with research positions at CERES, NOAA, and NCAR here in Boulder, and in Lindenburg, Germany, where he was the head of the Gruon Lead Center. This center manages the global upper air network of calibrated soundings to provide long-term, high-quality climate data records from the surface to the lower stratosphere. Currently, Holger's research interest at EOL is studying processes controlling tropospheric and stratospheric water vapor, temperature, and ozone in the troposphere and stratosphere using radiosondes and dropsondes. And that is exactly what he'll be talking about in his seminar today, which is titled Understanding Climate Processes in the Upper Troposphere and Lower Stratosphere Through Balloon-Borne Observations of Water Vapor and Ozone. We using Slido to pose questions, which you can type in at any time during the seminar. The Slido window is located below this presentation screen. Do not panic if you do not see your question pop up immediately. We archive all questions until the end of the speaker's presentation, where they will be revealed during the Q&A portion of this talk. Dr. Holger Vömel, we welcome you, and the virtual stage is now yours.
Thank you, Jackie, for this very kind introduction. Before I start on my talk here, hang on a second. Before I start, I would like to acknowledge a bunch of my co-workers, current and former co-workers, who contributed a lot to the data that I'm going to show. Most importantly, Rennie Selkirk and Ryan Stauffer from NASA Goddard, and in addition, my colleagues from the University of Costa Rica, Jorge Andres Diaz, Ernesto Corrales, and Alfredo Alan. I'll show a lot of their data. I would also like to acknowledge my former colleagues from Lindenburg, Ruud Dirksen, Tatjana Neber, Susanne Meyer, Marion Fiedler, and Michael Sommer, Peter Oelsner, who have helped build up the Gruon network, GCOS reference upper air network. And at the very end of the list, I'm not going to go through all of them. At the very end, I would also like to acknowledge Stephanie Evan from the Maido Observatory at Reunion Island in the Indian Ocean, where I will show a little bit what has happened there in the last few weeks, which is actually quite interesting. So just to guide you through my talk, there's a few key questions that I would like to ask. And the first one is a simple question: how much water vapor enters the stratosphere? That's an age-old question, and we've come a long way, and the Bloomborne observations certainly helped a lot. So the second question then is, well, how much does stratospheric water vapor change? What are the long-term trends and variabilities in the stratospheric water vapor, again, from balloon-borne observations? Well, but before we can answer any of those questions, we first need to look actually how do we measure stratospheric water vapor? And so I'll actually start my talk with the last question and then work my way forward. So let's first look at how do we measure stratospheric water vapor. There's, of course, the large global observing network coordinated by WMO. And here I pulled one nice slide from the WMO website, just showing what all of sorts of measuring systems there are. But most of them are actually for tropospheric observations. If we focus on what we have to measure the stratosphere, a lot of them actually drop out. So we're basically left, of course, with satellite observations, high altitude research aircraft, and balloons. And obviously, I'll focus here on balloons. But there's also, let's look at what capabilities actually we do have relative to profile even in the stratosphere. So this is a slide from the from NDAC, the Network for Detection of Atmospheric Composition Change, that has is working on a water vapor strategy to combine water vapor observations in the atmosphere. And so here we came up with a slide that just covers the altitude range of the different techniques within NDAC. And if you look at 15 kilometers and higher, you're basically left with in situ measurements from CFH, cryogenic frostpoint hygrometers, and research aircraft. All the others don't reach to that altitude. And of course, then you have your remote sensing instruments, and that is satellites. Most importantly, the microwave limb sounder on the AURA satellite, which has been up now for almost 18 years, so quite a while. So satellites, of course, have the great advantage that they provide global coverage. And the AURA MLS instrument is excellent that it actually gives daily global coverage. Other instruments like the ACE FTS or the ODIN SMR only give occasional measurements, definitely do not give global coverage daily. The big drawback, of course, they have poor vertical resolution, especially around the tropopause where you have strong gradients, and they require validation from in situ measurements. And of course, the current challenge is that all of the satellites measuring stratospheric water vapor are well past their end of mission life, and some of them are facing end of life fairly soon. So in the next few years, we will have much decreased stratospheric water vapor observations from satellites. Aircraft, high altitude research aircraft like the NASA ER2, WB-57, or in Europe, the Geophysica, Global Hawk used to be in this game, no longer is. These platforms, they're great for process studies using high quality measurements of many parameters, but they're poor for global coverage and they're poor for long-term measurements. These campaigns are very intensive, and so you only have limited times and regions where these can be conducted. Balloon-Borne soundings, they're mediocre for global coverage. We have some stations across the world, and I'll show some map, but they're great for vertical resolution and long-term programs. The longest one here in Boulder is now over 40 years old and still keeps going. So these are really important measurements. A big drawback, of course, is that the instruments are often lost and require careful calibration and preparation. Aircraft like our own NCAR G5, even though it's a high altitude research aircraft, just doesn't quite make it high enough. In the tropics, it still flies in the troposphere, and the polar regions, it actually does enter the stratosphere, so you could give us some measurements there, but it is a little bit limited in altitude range there. So there's actually, in effect, only 3 aircraft for this kind of work. So let me focus on the Bloomborne instruments, and most importantly, the cryogenic frostpoint hygrometer. Here's a picture of a balloon launch, Ernesto Corrales of UCR and San Jose, Costa Rica, preparing a frostpoint launch a few years ago. And there's a lot of manual work in preparing these instruments and launching them. And please keep that in mind. Every data point I show in later slides require an operation like this one here that Ernesto does in Costa Rica. They're very labor intensive, and in particular, really labor intensive for high quality measurements. Just let me explain a little bit how the instrument actually works. And it's important to understand the accuracy and the uncertainties and stability of the instrument. So the cryogenic frostpoint hygrometer is based on a chilled mirror instrument. So chilled mirror technique, where you have a mirror that is cooled such that a frost layer forms on that mirror. An optical detector senses this frost coverage, this frost layer, and regulates the temperature of the mirror such that this frost layer remains constant. If that's the case, if that frost layer doesn't grow or doesn't shrink, it's in equilibrium with the gas phase above, and you only need to know its temperature to calculate what's the partial pressure above that frost layer. So the essential measurement is actually only a temperature measurement of that mirror. And there's a thermistor embedded in that mirror, which is the only essential measurement that this instrument sends down. So it's important to remember the instrument is calibrated for temperature, not for water vapor. If we look at the uncertainty budget, how accurate is the instrument? The controller stability, I'll show that in a few slides, is actually the largest uncertainty source. I estimate maybe half a degree in frost point temperature. That's something like 10% or so in the stratosphere, or maybe 3% down in the lower troposphere. So it's actually quite decent. Then there are other parameters like thermistor calibration fit, thermistor calibration reproducibility, calibration of the reference thermometer, and a bunch of others that are fairly minor. Nevertheless, here I highlight first the thermistor calibration reproducibility. That's the one manufacturing aspect that comes into play here. The manufacturer really has to guarantee that every thermistor is calibrated the same to the same levels of accuracy. And this with every instrument that often gets lost. So it's important to understand the production process and here the calibration process so that the manufacturer can already guarantee that there's nothing funny happening. And so as part of that, with every batch of 25 thermistors, a small number of reference thermistors are calibrated over and over and over again. So it's the same thermistors that are calibrated. And what I show here is the deviation of an individual calibration run from the long-term mean calibration of these thermistors. And keep in mind, dotted lines that I show is 0.05 of a degree in temperature. So this is actually really good calibration for this sort of an application over a very large range from 0 degree all the way to -80. And if you look at it, you see a bunch of changes, bunch of wiggles, bunch of outliers, and some regimes are quite calm and quiescent, and others not quite, a little bit more wiggles in there. All of these show some of the details of how the production process changes over time, over years. This is really production over years. And however, overall, the stability is still well within the 0.05 or even 0.02 degree range. That's the reproducibility of the thermistors. And so that gives confidence that the thermistors that are put into the instruments are calibrated to that level of accuracy at the manufacturer. Of course, it's nice if a manufacturing process is stable over time, but just by experience, stations have found sometimes changes in instrumentation, not just here in Frostpoint instruments, also in other instruments. Here I focus on the Frostpoint. So it's really good if a station can actually verify the operation and the calibration of an instrument prior to launch. Remember, once a balloon instrument is launched, it's lost. And so if there's any questions coming up after the fact, it's really hard to do. So therefore, in Lindenburg, we actually came up with a ground check where we check the calibration of the instrument just prior to launch. And it's a very simple technique. The inlet tubes that are here indicated by these long solid lines there, that we stick a small fan in from one side, and we stick in a reference temperature and relative humidity sensor from the other end. The fan provides the ventilation over the mirror, and the temperature and humidity sensor measures the water vapor. That is actually quite a practicable approach for an operation that's quite labor intensive. And that way we have a humidity measurement right where the mirror is, right before launch. And here I show the actual pre-launch ground check at the Lindenburg over the last 7-8 years since we started that one. And it's not quite as good, obviously, as the calibration. Here we're only like within 0.3 of a degree. That's a scatter. But you have to keep in mind, this scatter here, the difference between the frost point and the ground check that I show here, is the combined uncertainty of both instruments. Because this reference instrument is not a high quality, super high quality lab instrument either, because that would be really hard to do. But just seeing that within this limitation of that approach, we are within 0.3 of a degree prior to launch. That's actually really comforting. And it also shows that we would be able to identify any systematic changes that might happen during production. So these two steps, manufacturer check and a manufacturer independent ground check, are really essential to guaranteeing a long-term stable record of water vapor measurements with instruments that get lost. So let's look at the other big term of the uncertainty budget, and that's the control of stability. The Frostpoint instrument, as I said, it regulates the temperature based on frost covers. So there is a dynamic response behind it that depends on a bunch of factors that are really hard to control well. So the control of stability is actually then how we can quantify this. And here I show two profiles from Lindenburg, two instruments on the same balloon. They actually see the exact same air, but they do have some different control response and therefore some different stability. The left one actually controls quite nicely. The right one, the blue, shown in blue, is a little bit more noisy. These are 1 second resolved data, and nobody claims that the instrument actually measures with a time resolution of 1 second for that in the stratosphere. That's probably pushing a little bit, but using that noise, we can actually make an estimate of what's the effective temporal or vertical resolution. So we can come up with a averaging kernel and apply that to the data. And on the left, you see both profiles averaged out, and you see those both, even though in the raw data, 1 second data, they're quite noisy. Once they're properly smoothed, they almost look identical. They almost see the exact same thing. The difference between the two is that the uncertainty is a little different between the two. Obviously, the red one I showed on the left before was a little bit quieter, and therefore its uncertainty is a little bit smaller. The blue one has a slightly higher uncertainty term. In parts per million, which is a common unit in the stratosphere, it's 0.1 or 0.2 ppm. So that's somewhere like 2.5 or 5% uncertainty just due to the controller response. In addition, this smoothing also allows us to quantify what is the averaging of that were applied to this data. So I call this the kernel width here, which ranges somewhere like 15 to 40 seconds in the stratosphere. And 40 seconds times 5 meters a second or so is like 200 meters effective vertical resolution. So somewhere between 100 to 200 meter effective vertical resolution with the average data. That's what we get out of it. The data that we currently provide to NDAC, the network for the detection of atmospheric composition change, they include all of this information. They include an estimate of this uncertainty, which I show in the middle, as well as an uncertainty, an estimate of the averaging, or i.e. the temporal or vertical resolution of the profiles. And so this way we actually know what's the vertical resolution and what's the uncertainty of each of those measurements. Also want to point out, this is a very generic, very boring profile, stratospheric water vapor profile that I show here, somewhere between 4 and 6 parts per million. So it's actually a rather boring task to do accurately over a long time. It's actually quite challenging. I point this out as boring because at the end I have some exciting stuff to show. In the tropical tropopause, it goes down to maybe 1 part per million. That would be, and our record that we have is 0.7 part per million, which is the lowest we've ever measured at the tropical tropopause. We also use these CFH launches to evaluate some radiosondes and how high they can measure relative humidity in the troposphere. Here is one nice example of a payload that actually has more than just one radiosonde. You see here on the left on this outrigger one radiosonde. There's actually another radiosonde sticking out even further than that. So this particular radiosonde has payload has 3 different radiosondes in addition to the CFH and an ozone profile. So that actually makes it quite efficient. In addition, of course, the Lindenburg has a great technology to recover instruments. So there it even becomes cost effective doing these things. So once you have a number of these profiles, you can actually do some statistics. And here I show a comparison between the Vaisala RS-41 radiosonde and the CFH that we have done at Costa Rica, where we've worked together with the Instituto Meteorológico Nacional, the Costa Rican Met Service, to do this in a comparison. And there we can show that the Vaisala RS-41 actually agrees with the CFH to within a few percent over the entire altitude range of the troposphere. This is really, really exciting and really extends the capability of what we can do with radiosondes, at least in the troposphere. We also used this to test another radiosonde, which has a similar sensor, slightly different implementation, the intimate IMET 54, a radiosonde from South Africa. And there we see a little bit of a altitude dependent bias. I should have pointed out, let me go one step back here. The dashed line there is actually the standard deviation of this data set. Here is a standard deviation of 18 soundings. So somewhere between 5 and 10%, that's the agreement in that statistical sense. With the IMET 54, that's a bit larger. So here we have a scatter of something like 30%. And that's the typical challenge with radiosondes, that their humidity sensors are not quite as good as those at the Frostpoint hygrometer, which is why we launched these Frostpoint hygrometers. So let's move to another question. Where do we measure stratospheric water vapor, and where should we measure stratospheric water vapor? The easiest figure to answer that one is the old paper from Alan Brewer, 1949, that basically highlighted how the global stratospheric circulation works, that air enters the stratosphere in the tropics, is then transported poleward and descends at the higher latitudes. And for me, it's still baffling that they came up with this circulation from a few aircraft-borne frost point measurements from England. This is really some ingenious deduction of atmospheric observations. But it also shows that it's really important to measure in the tropics. That's the biggest highlight. And for that purpose, we've actually set up the soundings of ozone and water vapor in equatorial regions, a project that ran until about 7 years ago, especially in the Indonesian region. We also started in Costa Rica in 2005, so 17 years ago, that we have routine measurements there, but we would probably need a few more. It's also important, stratospheric water vapor has a very long lifetime and small changes, so we need to measure for a long time. So here are the current stations that actually do measure water vapor. Boulder, I mentioned that before, operated here at NOAA, started in 1981. Actually, the first flights, I think, were even in 1980. Sodankila, Finland has started some soundings in 2002, Lauder, New Zealand in 2003, our solid southern hemispheric site, San Jose, Costa Rica in 2005, Lindenburg 2008, and so on. There were also many other campaign-based observations, and I'll show those here. The red highlighted stations are those that have ongoing routine observations, and all just gray dots are those where some campaigns have taken place, and particularly in the East, Western Pacific and Indonesian region, the SAUR campaigns. We got some very interesting results. Reunion Island, I point out, as our second southern hemispheric site. They're just starting up with frost point observations, and hopefully this year we can do some work to get them going for a long-term program. So how much does water vapor change? Dale Hurst at NOAA published this paper now 10 years ago, and showed some interesting increases of water vapor in the 90s, and then in the 2000s, it sort of stayed constant with some down and back up. through 2000 to 2010. I'm sure he's working on an update for this figure, but I've looked meanwhile at the data from Lindenburg, which I show here, which looks very, very similar. So we have the different altitude regions from 16 to 26 kilometers. Down low, you see more of a seasonal cycle still, so 16 to 18 and 18 to 20 kilometers, much stronger seasonal cycle than at the upper altitudes, in particular 26 to 28. There is much more interannual variation than seasonal variability. But where it gets really interesting if we compare the different sites. Costa Rica is our most tropical site, Hilo, Hawaii, slightly subtropical. Boulder, of course, our true reference site, and then Lindenburg for the last 10 years as well, 15 years as well. What's really interesting, Boulder at 40, Lindenburg at 52, here at this particular altitude region that I picked out, almost indistinguishable. A very good agreement between those two sites. They don't use the exact same instrument, they use the same technology. Boulder builds their own instruments still in-house. Lindenburg and the other and Costa Rica used the instrument from NCAR. Hilo, of course, is also NOAA GML site, so they also use the NOAA instrument. But so Costa Rica has the lowest measurements, strongest seasonal cycle. So clearly, this is the most tropical. And the more higher north you go, or more poleward you go, the higher water vapor. This increase is due to the oxidation of methane in the middle to upper troposphere, which then gets transported downward and is then detected here at these sites. So yeah, it is really interesting to see. To see the nice agreement here, another one layer up at 20 to 24 kilometers. Also want to point out, Lindenburg has these occasional periods where they're quite a bit higher than Boulder actually is. And the reason for that is that Lindenburg occasionally is under the polar stratospheric vortex in the winter. And that shows up in these long-term trends that we actually pick up air truly in the polar stratospheric vortex. And we've even seen occasionally a little bit of Arctic dehydration signals, just minor, but you can pick it up if you look closely enough. That's something that you would not see in Boulder. So it's really important to have these sites and this latitudinal coverage. And I just show this here as one example. I could have added Lauder as well, which looks somewhat similar. Well, the next question is then, how much water vapor enters the stratosphere? As I've shown the figure from Alan Brewer, of course, it's the tropics that's important. And so we need to look at, well, how do the tropics look like? And this is our data record that we have in San Jose, Costa Rica. And we see, of course, nicely a seasonal cycle in this 17 to almost 25 kilometer region. The minimum is at somewhere around the tropopause. I didn't put it on this particular slide. And if you look closely, you also see this minimum rising with altitude throughout the year. That was first discovered, of course, with the UR's halo measurement in the measurements in the early 90s, and was dubbed the tape recorder effect. For the younger folks in the audience, you probably need to look up what a tape recorder is and to understand where the term comes from. But we can look at this a little bit more closely if I do a seasonal average here. All of these data now are averaged into seasons, and I put the average tropopause in here as well. And so you see that the seasonal cycle actually for me always starts like September, October. This is when the seasonal minimum starts forming. It's most extreme in January, February, when you have the strongest minimum of water vapor in the tropopause, which then rises with the season. So we have a dry phase that rises and a wet phase that rises throughout the year. So this tape recorder immediately gives us also a measure of the rising air in the stratosphere as the air ascends above the tropopause. And that was a major breakthrough. In the 80s, there was still this puzzle, why is there a water vapor minimum well above the tropopause? At that time, it wasn't quite recognize here that this slow vertical ascent actually plays a very, very important role in this process. So that also means if we understand what's happening exactly at the tropopause, then we should be able to actually tell how much water vapor does go into the stratosphere. And so for that purpose, we actually, I plot here the data of exactly at the tropopause. Well, at the tropopause, what is the tropopause? I actually used the two different definitions, the lapse rate tropopause and the cold point tropopause. So basically, what's the coldest point in the temperature profile? And it turns out in the early parts of the year, that difference is not that large. In the rainy season in Costa Rica, June, July, August, September, there's actually a significant difference that the lapse rate tropopause has a slightly higher mixing ratio than the cold point tropopause. I also put here the tropopause saturation mixing ratio. So what would you expect if the air was saturated right at the tropopause? And you see there's actually reasonable agreement with the lapse rate tropopause, but not the cold point tropopause. And Laura Pan has used these data and some others as well to clearly show that there's a difference between the two, and that between lapse rate and cold point tropopause, there's still some interesting difference region that we can analyze further. But let me first look again at the relative humidity. So here's just relative humidity. So basically taking the measured mixing ratio divided by the saturation mixing ratio. And this throughout the entire profile for the entire data set in Costa Rica. And you actually, the first thing that really sticks out is just nicely see the rainy season from May through October and the dry season from November through April. But you also see that in the tropopause region, 17 kilometers roughly, you're always close to saturation. However, when I do this sort of averaging, here I've just done binning by altitude, which is probably not quite appropriate because I bin some altitudes that are in the stratosphere and mix them with altitudes that are in the troposphere and some that are exactly tropopause, throw them all the same, and so it doesn't quite average out properly. So if I really want to look what's happening at the tropopause, I should probably do it all in tropopause relative coordinates. And so that's what I'm doing here. I shift all profiles so that they all line up at the tropopause, at the climatological mean tropopause. So the altitudes are now a little shifted, and voila, you see you always have a maximum exactly at the tropopause throughout the year. And so that is the fundamental basics of our tape recorder effect that we have. If we now look again here at relative humidity over ice from what I just showed here, we see that the lapse rate tropopause is just about within, give or take 5% relative humidity at ice saturation, and that throughout the year. Whereas the cold point tropopause is a little bit below. So the cold point tropopause at Costa Rica is not quite saturated throughout the year. That's actually an interesting question because that really raises a question, well, what does set that particular value at the cold point tropopause? Well, it turns out that Costa Rica is not quite sufficient to explain the water vapor at that level, and that there are other regions in the world that play a role there. And we all know, most notably, the Western Pacific region. So if we wanted to understand exactly how this cold point tropopause works at Costa Rica, we would need to measure in the Western Pacific region, which has the coldest tropopause temperatures globally. Unfortunately, we do not have any monitoring station in that region at all. That was the reason why the SAR campaigns focused on the Western Pacific. Unfortunately, only in the months January and February, so I didn't include them here because we don't have a full seasonal cycle. But for that particular reason, it would be really nice to have a routine station in the Western Pacific, and hope we're working on getting one spun up, hopefully in a year or two, but that still takes some work to get done. So now we know how much water vapor enters the stratosphere. Really? Let's look at that question again. And the reason why I'm hesitating a little bit, we've done, all of this was based on the assumption that air enters the stratosphere quite slowly, which is not always the case. And that's the really exciting stuff that's happening right now. There was this eruption of the Tonga Hungaha volcano in the Western Pacific region, just a little off the island of Tonga, which was heavily impacted by this volcano. This was one of the largest eruptions, maybe of the last 100 years or so. Here's a satellite image I found on Twitter, actually with some indications of what altitudes are. An umbrella shield, a volcanic plume shield of something like 35 kilometers, spikes maybe up to 55 kilometers. All of these needs to be confirmed with other measurements, most importantly, Calypso as a space-based LiDAR. There's a lot of work going on right now. But a volcanic eruption that throws up air up to 35 kilometers certainly is bound to have some impact on stratospheric water vapor. If we look at where this air actually went, here's a simple trajectory analysis I just did. Right there in the center at the right end of those trajectories, that's where the eruption was on the 15th of January. And a forward trajectory brings it pretty much, just transports it westward and very close to the to Reunion Island. Reunion Island is one of our monitoring stations, and NOAA and the University of Houston scrambled a rapid response campaign in cooperation with the MIDO Observatory at that island and launched a bunch of balloons actually into this volcanic plume as it went over. Here is what a very benign profile looks like. That's sounding from 3 years ago, and I'm actually also adding Aura MLS data. Those are those solid lines, ziggity-zaggity lines there. And you see a very nice agreement between a frost point measurement and the satellite. I wish I could show you the frost point measurements for this overpass over Reunion Island. I can't yet, as we are still working on the analysis and what it all means, but I can show you the MLS data. And the Aura MLS data for when the plume passed over Reunion Island showed mixing ratios up to like 100 ppm. This is a factor of like 20 or so above what's a normal stratospheric water vapor. So there's a lot of work going into what does that mean? What do the in situ measurements tell us? In situ measurements do show even higher levels than that. So they certainly have a very huge impact on the stratosphere going on right now. And unfortunately, we just had a science meeting last week, and so we're still working on analyzing this data in great detail and figuring out what it all means, and want to put a nice story together. So with that, I'd just like to ask you to stay tuned for really, really interesting and exciting results that will come out of this study. So we're actually working on to quantify the amount of water vapor that was really injected by this volcano and what the impact of these huge amounts have on the plume dynamics and what the medium-term impacts will be on the stratosphere and the global climate. So that's really exciting and really thrilling, and I wish I could show you more, and hopefully in a couple months, 3 months, whenever we have something more to show, we'll get some really fascinating stuff coming out of this. So with this, I will leave a little bit time for questions, and just summarize up that high quality stratospheric measurements require careful preparation and manufacturer independent ground checks. Keep in mind that every data point that I showed you on my plots here is one single instrument, where an operator launched one instrument that possibly most likely was lost. So a lot of work goes into making sure that these instruments work the way we hope they work. Recent trends of stratospheric water at several stations are consistent with each other, and over the last 20 years don't show any significant increases or decreases, just some seasonal and interannual ups and downs that generally correlate well with the tropical tropopause. At Costa Rica, we do show that the relative humidity over ice is at the tropopause on average is very close to 100%. So that means on average, the tropopause temperature is actually a fairly decent proxy for water vapor, for the amount of water vapor that enters the stratosphere. And that's one of the fundamental assumptions for any of the global models when they model stratospheric water vapor, that the water vapor is really set at the tropopause temperature. Now, there are some subtle details, and most importantly, this difference between cold point and lapse rate tropopause, and the difference between the regions. We don't have measurements in the Western Pacific, which is something we definitely need, and we're working on to get spun up. And of course, rare large volcanic eruptions can inject huge amounts of water vapor into the stratosphere, which is the first time we've seen that, not the first time that it probably happened, but the first time that it happened while we had the technology in place to actually observe it. And that's really exciting. And so more details will follow soon. And with that, I'll end here and leave some time for questions. Thank you very much for your attention.
Thank you, Holger. As a huge fan of sounding observations, I really enjoyed your overview of the instruments and its capabilities. We have time for questions. Holger, I applaud you for keeping well within the hour. May I remind the audience to please use the Slido interface below the presentation screen to ask your question. And I'm hopeful that audience members are judiciously crafting and typing questions in Slido. And we do have a question from Julio Backmeister, and he asks, how do these tropical profiles compare with satellites, example MLS?
Yeah, let me just show that one slide that I had shown already, which just symbolizes and answers that question. This is just a snapshot from Reunion Island 3 years ago, and you see an excellent agreement between the two instruments. Dale Hurst actually wrote a paper a few years ago where in version 4 of the MLS retrieval, drift was observed relative to the Frostpoint instruments, which then actually prompted the MLS team to go back and look into great detail what is going on with the instrument, what's going on with the retrieval. And they actually updated their retrieval, taking account some of the effects they've learned in the meantime about the aging of the instrument. Keep in mind, the instrument is now 18 years in space. What I show here is the current version 5, which again shows a very, very good agreement between the Frostpoint instruments and MLS over the entire data record. And Jackie, you're muted.
Sorry about that. I shall keep myself unmuted. Thank you for that question, Julio. We have a question that I am highlighting by Brian Green, and he asks, can you use the water vapor tape recorder to estimate the total upward mass flux in the tropics and get an estimate of the strength of the Brewer-Dobson circulation?
Yes, absolutely. You can do that. Bill Randall, I think, has done a fair amount of work on this one. I can't remember. Sorry, I'm just looking the other name here. But yeah, there are several people who are working on exactly this topic. And yes, absolutely, you can use the tape recorder to look at that. One of the challenges, you have to look at some of the diffusion coefficients, vertical and horizontal diffusion, which messed that up a little bit, makes it a little bit more complicated. But yes, it can be done. I'm not quite sure whether anybody has done it just using the Frostpoint data. Typically, it's done either in reanalysis or in the MLS data.
Thank you for that question. We have a number of questions that are following. Our highlighted question is from Andy Hemsfield, and he asks, are there any measurements in Costa Rica that have coincident LiDAR data to see if clouds are present?
Andy, please give me a LiDAR. I would love to have that. No, unfortunately, we do not have a LiDAR present there. In fact, the one answer for that one is what they do, for example, in Lindenburg. In Lindenburg, we've started a program where there's 2 monthly soundings, one during the day, one during the night. The nighttime sounding has a cobalt backscatter instrument on it. So from that, we actually have a very large data set of in situ backscatter measurements and frost point measurements, which is actually a little better than having a LiDAR. With the LiDAR, the big challenge is the horizontal drift. And at the tropopause, you might be off by several tens of kilometers compared to your LiDAR. So it's better to have it on the payload. And in Lindenburg, we have a data set for that. Some of the soundings in the Tibetan Plateau have cobalt backscatter instruments on that. Reunion Island also had some backscatter instruments a few weeks ago. But in Costa Rica, unfortunately, we do not have any cloud information with our data. And that's one of the big shortcomings. If we had the funding, the long-term funding for it, we would absolutely do it.
Need for observations continues. We have a question from Peter Sullivan who asks, can you infer vertical velocity from these measurements?
Simple answer, yes. I haven't done it yet, and I'd be happy to share the data. In fact, I mean, you can pick them up at NDAC, at the NDAC archive and do it yourself. But yes, absolutely, it can be done.
Thank you for that question. We have a question from Andrew Gettleman who asks, there does not seem to be a recent trend in stratospheric water vapor from Boulder or Lindenburg. Is that consistent with methane trends or tropical tropopause temperature trends, if any?
Andrew, I would give that question back to you if we could have that in the room and I could get the answer from you. That is a good question because methane actually is increasing, and so we would expect some increase, which we don't really see. So that's a very, very good question. And that probably takes full reanalysis data where you look at full transport, full methane oxidation, look at a full tropopause temperature trends. But one of the key statements that I can show here is that the Boulder record is not unique. What we see in Boulder, we see in Lindenburg. So it's really the Northern Hemisphere that shows those trends or lack thereof. And so we have a very solid database to actually tell this is what stratospheric water vapor is. And now it's up to the modelers to figure out, well, how does it jive with the methane oxidation and the increasing methane trends and the tropopause trends. And again, if I had Western Pacific water vapor data, I would love to add that into that mix as well.
Thank you for that question. Our next question comes from Roy Rasmussen, who asks, the CFH comparison to operational sonde water vapor suggests that there may be impact on the reanalysis data. Is this true? And if true, what kind of impacts would you expect?
This is actually a very good question. And that's one of the big challenges that the community has right now with radiosondes. So I showed actually a comparison of 2 different radiosondes, one that's actually excellent, one that's so-so. I could have shown some comparison with some other operational radiosondes that are very limited, to express it politely. The big challenge for the operational reanalysis is to understand which radiosondes are actually being used. And there's been a lot of effort going on in changing the data formats, how radiosonde data are being transmitted to the GTS and how they're being assimilated at the numerical centers, and how they can actually tell the difference between the two. This actually does play a role in a lot of things, but right now you have two different data formats that are being sent from operational radiosondes. One's called the temp format, one's called the buffer format. The temp format has very coarse resolution, doesn't tell what a radiosonde it is, and has very limited metadata. The buffer data, if the station properly formats it, then does send that information on to the numerical sites. So they need to know that information. Often there are changes in equipment that is not being passed on. So that's one challenge. The other challenge is that often the data centers actually start to ignore data above, let's say, 300 or 200 hectopascal, because the humidity there historically has been highly unreliable. And so there is a threshold set that says, well, above that, make the uncertainty for these data so large that they do not have a large impact anymore. So that means operational radiosondes in reanalyses probably do not play a large role in the upper troposphere, and definitely not in the stratosphere. They probably could if the data are properly sent to the data centers, and if the data centers can make use of that information. That's a really big challenge, and there's been a lot of work going on to improve that, and it is still not done. Right now, I think it's maybe half of all stations globally that send data in buffer, and the other in temp messages, and even all buffer data are not with the full metadata that allow you to make full use of that. So as I say, right now, I think the impact in reanalyses in the upper troposphere is probably still limited. It could be stronger.
Thank you for that question. We have a question from Minghui Diao, who asks, it was a lot of hard work to provide accurate water vapor measurements with consistent calibration, and your results show that the efforts were well worthwhile. Could you comment on if there is any future plan for intercomparisons between aircraft water vapor instrument and balloon sensors at EOL?
Right now, I'm not aware of any particular efforts, and of course, I know you're very interested in the pixel instrument, our water vapor instrument on our G5, and that is a very good point. This intercomparison of instruments is really, really important. If you can intercompare instruments and you find that they agree, you get a warm, fuzzy feeling, and you can move on with your scientific analyses. If you find disagreements, then it's a lot of work to get them into agreement. So the MLS team, for example, had a big challenge when Dale Hurst published that drift between the Frostpoint and the satellite instruments. So that created a lot of work. And the same here with the aircraft instruments. It gives you a warm, fuzzy feeling if you can intercompare with a different platform and see the same results. Then you have very solid observations. It is currently not in planning, not to my knowledge, and we could probably continue the discussion and actually push that particular topic a little bit further.
Excellent question. Thank you very much for asking that. We have one question that has come in from Tammy Weckworth, who asks, thank you for this presentation, Holger. Are there previous measurements of water vapor injected into the stratosphere from volcanic eruptions, and how long does the impact last?
The answer is no, and we don't know. So the last big one of that caliber was probably Pinatubo about 30 years ago. And that was just the beginning of the halo period, which caused a lot of problems because of the aerosols. SAGE-2 was the other main instrument measuring stratospheric water vapor at the time. And again, there was a lot of interference with the stratospheric aerosols, which means the actual water vapor measurements in the eruption plume were just deemed unreliable. And they probably were unreliable just because of the really difficult spectroscopy and all the other crap that you suddenly have in the atmosphere that wasn't there before. And there wasn't any other satellite of that caliber that has done anything to the stratosphere. How long does the impact last? Well, we can only go by Pinot-Tubo, and that was several years. So that, however, remains to be seen. Because right now, it just happened, 3 weeks ago. That's why I was so hesitant in giving any kind of specifics. We're working, well, how much SO2, how much ash was thrown into the atmosphere, into the stratosphere, how much water, what does it do to the duration and the formation of aerosols, sulfuric acid aerosols. So there's a lot of open questions, and it's completely new as far as our observing capabilities. So since satellite meteorology, this is probably the first real big one. And then, of course, as I pointed out, it was really fortuitous that the eruption plume went over a prime station that has a lot of technology to observe the stratosphere. They have LiDARs there. There was the deployment from NOAA in Houston. There, they had the Frostpoint soundings there. So there's a lot of measurement, valuable measurements that will come out of that, that can answer that question. And it's completely new. I just looked at some old modeling papers, and they all do hand-waving assumptions on, well, it could be like this, could be like that, but we've never seen anything. And so this is a really new thing, and that's really exciting.
Thank you. Thanks, Tammy. With no further questions, we are near the end of the seminar hour. If you are interested in Dr. Holger Vömel's presentation and have further questions, please reach out to him via his email, which is provided on the seminar flyer. On behalf of NCAR and EOL, I would like to thank Dr. Vömel on his excellent presentation evaluating water vapor balloon-borne profile observations. Thank you, everyone, and have a good day.